I'll actually spend a few slides explaining, like, on a very high level technically how IPC works, and then we dive into comparison to other L2s. So these were our goals, roughly speaking. So let me go through them. But actually, one of the first goals is to have scalability of a blockchain network to billions and trillions transactions per second. Yeah, like you're thinking at that level. Okay, we are not there, but we are getting there. So this is the first motivation. So basically, we need to have this on-demand horizontal scalability for Filecoin and other blockchain networks at Web3 scale. And then we wanted, like, this is not a requirement, this is more of a architectural design, but then we didn't want a single layer of scaling. Like, we wanted actually to build a hierarchical solution that can scale to, like, if you have a gaming L2, then you basically spawn an L3 with a particular game, which is maybe ephemeral and short-lived, and then you go back to an L2 and all sorts of stuff. Like for storage, you might have these regions and like continents that Juan was describing yesterday and so on, right? So it should be like it's somehow lends, it's like the goals lend themselves to the solution in some sense. So IPC is based on proof of stake sidechains, and I'm going to dive more deeply what I mean by this. And there is this decentralization, scalability, security trilemma, right? So basically, as you are improving the performance of a chain, then it's usually not as decentralized as an L1. So there is a trade-off once you start implementing more efficient protocols. And we need to basically get best of the world. So if something goes wrong on a subnet, we want to essentially firewall this and basically for this problem to stay in a particular branch of the IPC, this hierarchical tree. And not only that, but we actually want to leverage the security of parents to basically boost the security of child. And you will see briefly how this works. We also wanted like all these subnets not to be disconnected from each other. Like there is this concept that subnets store some information in their parent net for security, but that they also able to leverage the tree of subnets to communicate among themselves. So what the protocol has inherently built in is this subnet interoperability where you can send funds and state in principle from a subnet to another subnet, not directly, but actually going through the tree. So this reminds, like, one of the examples that I usually have is like when you send, in current banking system, when you send from a given account to another account, right? So what happens in the background is basically, what you don't see is that there is actually a high-level messaging network, like Swift, on which you basically address the subnet, and then you have a transaction that directly goes to another bank, which you can think of a subnet, right? So we need to have something similar, which with user experience that's basically seamless. We wanted to use basically FVM and FEVM, so we are building and basically going a bit behind FVM. So our solution, as you will see, is based on 2 smart contracts that live on Filecoin mainnet, and the same smart contracts are used in subnets to facilitate the communication among subnets. And in particular subnets, like currently we're going to ship end of this year, beginning of next year, we're going to ship on Tendermint blockchain node. So basically subnets are going to run Tendermint consensus protocol, but this is temporary. So we have work to modularize consensus protocol, and once we move to this yellow runtime that we discussed, we are going to have the ability to change completely consensus protocols on particular subnets, and to tailor basically consensus protocols within a subnet to a particular use case. So this is like, in a nutshell, how it works. Imagine that you have Filecoin with 30-second block time, and like, then you have, for example, Saturn CDN L2, which runs on its own subnet and periodically checkpoints information to Filecoin mainnet, leveraging the security. So if something goes wrong on this L2, basically this storing the Merkle root of the state here prevents that, like, these guys, if they go rogue completely, can can basically revert the state that was already stored there. So this is the essence of these checkpoints, plus we use checkpoints to transfer the state across subnets. And this is hierarchical and recursive, so basically if you have data center level subnet in future, this can go to the millisecond latency, and the communication basically goes like this. One of the keys is that we don't need, for example, once we launch, and actually we have an alpha based on Lotus-based IPC, Lotus-based blockchain node. We have IPC already deployable in mainnet, and we didn't have a FIP for that. So why? Because everything is governed by two userland smart contracts, so which you can deploy now and have your own IPC tree, and everything lives in userland. Everything lives in FVM, FEVM land. Okay, so how do you spawn a subnet where you just add, actors are actually on next slide, but basically you agree with a couple of other token holders, you stake, initial stake in the smart contract, and basically this spawns a proof of stake sidechain or a subnet, which is your L2. And basically anyone can do this, like it's totally permissionless in that sense. And from these you can recursively spawn L3 subnets and so on. Okay, so these two smart contracts are depicted here. So there is a gateway actor. There is one per subnet. So in mainnet, we have one instance of a gateway actor. And then for every subnet spawned from the mainnet, we have one subnet actor living on the mainnet. And this subnet actor that lives on the mainnet is basically connected to the gateway actor on a particular subnet. So there is a mapping, like so one gateway actor for the rootnet. And then for each subnet, you have one instance of a subnet actor, which basically talks to the gateway actor, which lives on a subnet. So this is how the communication goes. And these are two smart contracts, so they're written in Solidity. So practically, you can deploy this on Ethereum as well, or any other EVM-compatible chain. So that's a nice thing, right? One thing is how, okay, I mean, these smart contracts live on these subnets, as I explained, but what hooks everything together, and this is a bit of an artifact of our Lotus-based approach, because this IPC agent is coded in Rust, and it's basically separate from subnet nodes, right? So you should think about it as one participant of like an SP, for example. If an SP runs not only a full node, but like a miner on L1, and it runs a validator on a subnet, what it would need also an instance of an IPC agent that connects its nodes and basically allows transactions to be submitted from one subnet to another subnet. So IPC agent instance is per participant. There is no centralized instance of agent globally. Like each participant in the network runs its own instance of an agent. Okay? And there are these cross-net messages, right? So two basic concepts, and I hope, Alfonso, you will dive in the demo in more details. So there are top-down messages and bottom-up messages. So top-down messages serve to, because in IPC, it's really hierarchical. So whatever state change happens on a parent, it's just adopted by a child. So children subnets need to observe what's happening on a parent net, and basically they're downloading the state to a subnet. So this is done by these top-down messages. So syncing with parent. And bottom-up, well, parent doesn't necessarily care about children, so children need to tell the parent what's happening on child subnet. So essentially, we have these checkpoints, which are usually signed, which are not usually, which are signed by a multi-sig of validators on a proof-of-stake sidechain, which basically constitutes the subnet. And basically, they are propagating upwards. This is the green line here. Okay, so this is very... Do you have questions? So on a very high level, how this works and how this is structured, right? So again, to summarize and to stress once more, what are we talking about? So IPC forms a recursive tree of proof-of-stake sidechains. So staking is done starting from an L1. And we are currently, like in principle, you can do staking in like ERC, FRC tokens. But like we are currently coding only for staking in Fil. Or basically, if you think of a native token in L1. And then from then on, you can, of course, spawn additional layers, L3s, and whatnot. You don't have to have proof of stake. Like you can have a BFT protocol, so one validator, one vote as a special case, but that's a special case, right? In principle, these are proof of stake subnets. About data availability, this is a popular question, right? So what happens is that subnet transactions, they stay on a subnet. They are available because they are replicated by the consensus protocol among validators. We don't have a centralized sequencer like rollups, right? So as the subnet operates, it basically, the consensus protocol replicates transactions across the validators of a subnet. And checkpoints are, so checkpoints and not input transactions. So we'll have the comparison to rollups later on. But what happens is that input transactions stay on a subnet. Security, like what is the security? Okay, we have the firewall property. If a subnet goes rogue, this doesn't propagate to the parent net or other. So if L2 goes rogue, this doesn't propagate to L1 or other L2s. But it affects children, L3s, and whatnot. But there we use also checkpoints and slashing on parent net. So slashing on parent net is more powerful than slashing on L1 because if you detect equivocation on a subnet, you have basically higher authority to which you can submit the proof of equivocation and slash the collateral which lives on the parent. So this disincentivizes misbehaviors and strengthens the firewall property, essentially. And in principle, if you heard about escape hatches on rollups, we can use the same principle. We are not coding for that now, but it's on the roadmap. We have cross-subnet communication. So you can address subnet from a subnet for cross-net fund and actor state transfers. And it's really decentralized scaling. So one of the governing principles was do not use any centralized component. And this is one of the key differences to other approaches. Okay. Any questions so far? Okay. Okay, but what about this and that, right? So in Ethereum, you have tons of projects which are usually classified as validiums, rollups, plasma, state channels, sidechains, any combination thereof. In Bitcoin, you have, of course, Lightning Network. Then you have tons of other scaling solutions. And then you have, like Polygon has its own scaling solution. Avalanche has its own scaling solution. Internet Computer has its own scaling solution. So how does this all work? So the next 10 minutes or so, I'll try to actually give you a mind map how I would like you to think about this. So let's start from Ethereum ecosystem. So in principle, we already talked about where IPC keeps the data, like input data. And in Ethereum language, this is Ethereum language here, and other ecosystems have different languages, especially Bitcoin, but like this is starting to be prevailing in the whole crypto world. So rollups are basically scaling solutions in which the L2 input data lives on the mainnet. So it lives on L1. So data availability for L2s is provided by an L1. So this means data on chain. And then depending on how you prove the state of an L2 to L1, we talk about fraud proofs, optimistic rollups, and Snark and Stark zero-knowledge-based proofs. We talk about zero-knowledge rollups. If the data is stored off-chain, so not an L1, but either on L2 itself or somewhere else, Ethereum language talks about Validium and Plasma, depending on, again, how do you prove fraud proofs. Is this clear? Okay. Now, I'm not going to adhere to Ethereum police usage of word L2 because they, for example, say Validium are not L2s. But rollups are L2s, and it becomes difficult to navigate, right? So we are going to loosely, in Ethereum sense, talk about L2s. And even though Ethereum, like documentation says that Plasma is more secure, no, Validium gives more security than Plasma, but Plasma would be L2, but Validiums are not, so forget about this. Like, okay, so L2s are more generally any scaling solution that comes beneath, right? And as this other post says, like people shouldn't be getting triggered over the name of the things, right? And by the way, so for example, Plasma was previously, this is 2018, called SNASMA and stuff, but I think Ethereum, so this is about naming that Nicola complained, like you need to have consistent naming and it's difficult to have a mental model like what things mean. But I think we are kind of converging and this is the basis of my future comparison, which is going to come in next slides to basically all this stuff and IPC. So for Lightning Network, which is probably the most used L2, well, at least in the Bitcoin ecosystem. So the goal was to turn Bitcoin not only be sound money, but actually to be usable as a global payment system. Because the main problem with Bitcoin is, of course, scalability. You cannot, I mean, even if this is sound money that's going to be used by everyone, which is the Bitcoin basically goal, you cannot use it as a payment system because you cannot fit all transactions of all people in the world on an L1. So why? Because this impacts decentralization. So if you just enlarge the block size, then the blockchain becomes bloated. And Bitcoin already had forks in 2017 on this. And if you didn't read this book, please read it because like it's a great read, these block size wars. So what you want for decentralization of L1, you want to keep L1 as small as possible. So anyone can run a full node, essentially. Which means that you need to push scaling to L2s. And, well, Lightning Network has its own challenges because it takes one L1 transaction to open and close the channels and so on. But without diving into that, Bitcoin ecosystem has also a bunch of sidechain solutions, especially if you need smart contract programmability, which is not offered by Lightning. And basically, if you look at L2 scaling at Bitcoin, this is usually sidechains with smart contract programmability. And this is a brief overview of how it looks in the Bitcoin ecosystem. So without diving too much into it, these are independent L2s, right? Which do not really operate with each other, right? So like these are independent scaling solution, which is one chain only in each case. So this is rather different from our goals, as I showed you previously. So in Ethereum world, this is just a snapshot I took yesterday from L2Beat. There are not too many sidechains. There are some, but actually the most popular L2s are, as you see, rollups and Validium. So this Optimium is a version of Optimism, so it's again rollup based and so on. And essentially what's interesting here is that Ethereum really favors rollups. But rollups have this centralized sequencer, and I will basically dive into this a bit in some future slides, but this is not really a scaling solution because of several things, because of centralized sequencer, and because of the fact that rollups really pile L1 transactions to the mainnet. So if you're talking, again, recall our goals, it's billion transactions per second or trillions. You are not going to put billions and trillions transactions per second on an L1, like, that's clear. Which makes it interesting for IPC, and this is like a project that I just want to briefly mention. It's like turning optimistic rollup sequencer into proper L2s, where essentially in this project, we are trying to work with an optimistic rollup and to turn it into Plasma-like solution where we store input data on an IPC L2. But this is just a teaser, right? So, okay, technology-wise, sidechains, which I mentioned, are related to IPC. because sidechains was the definition. So basically, sidechain connects to another chain called parent chain. We have two-way peg, which allows fund transfer from one to another. So IPC is that and a bit more. So it is a network of sidechain protocols with additional features. So there is a hierarchy among subnets. And this hierarchy is leveraged for security. There is native cross-net communication, and I'm highlighting that IPC is FVM and IPLD based. So regarding Plasma, so what's Plasma? Just briefly again. Plasma is like sidechains, but there is information that's put on the parent chain. So I took this from the documentation of Plasma. So, however, unlike sidechains, the root of each Plasma chain block is published to Ethereum in this case, so L1. And block roots are basically little pieces of information that users can use to prove things about the contents of the blocks. So it's actually what we are doing in IPC. So if you think in this terminology, so IPC can be classified as a Plasma protocol with the additional features. Again, hierarchy, I'm repeating this, but this gives you just delta with respect to different technologies, right? So you could see it as Plasma if you like this, right? But it also has hierarchy among subnets, native cross-net communication, and it's FEM and IPLD based. So validiums, and IPC is currently not a validium because we don't use Starks and Snarks of any kind at the moment. But it could become one. And like we could use, so currently we are using multi-sigs and for slashing we use fraud proofs on parent net, but conceptually nothing prevents us from using Snark and Stark state proofs a la Validium in future. So this is possible and it could be our focus in future. It's not now, but it could be. Okay. About rollups, now IPC is not a rollup, and I would say it could be, but it doesn't plan to be. And again, this is what I mentioned. So why do we really not plan to be? Because rollups are simply not a trillion transactions per second scaling technology. And by recursion, if you start posting everything on L2, then an L3 posts everything on L2, and L2 posts everything on L1, so basically everything pops up to an L1, which means that you are storing these trillions transactions on an L1, which means that this is not a decentralized way of scaling things, again, because the L1 gets bloated. And if you talk about trillions of transactions, then it's not even centralized way of scaling, unless you have a big brother supercomputer that basically stores everything, all the transactions in the world. So this is just not gonna fly for our goals. But again, as I mentioned in that sashimi slide, IPC could be used to properly scale rollups by turning them into sort of Validium and Plasma by actually having IPC store act as a data availability layer for current rollups. Yes?
So if you have rollup and you create a hierarchy, So if you have a rollup and you have a hierarchy of rollups, would data from L3 end up on L1? I think no.
I think yes, because like,
Whole data, right? Whole data is not.
well, it depends how you implement it, right? But like if input transactions of a child end up on the parent, then you could argue. It's about naming, right? So if you, I'm arguing that you shouldn't be doing that. It depends now how this is called. But like, I would just say let's make sure that we don't post all transactions on L1, right? So if we don't do that, then I would be more permissive of this, like more acceptive to this technology, but not at the moment, right? So it's like a partial scaling solution, fine, but not for this goal, right? So not for trillion transactions per second. Okay, now there are other solutions which are actually much more similar to IPC than rollups and others, right? So Polygon Supernets launched earlier this year, and it's rather similar to IPC. So I tried, basically if you see this, I don't know how visible is this, but Polygon proof of stake chain has a bridge to Ethereum, and then Polygon supernets are, if you consider Polygon proof of stake as L1, just because this is a bridge, so they should be peers like here, then basically this is just L2s. So there is no hierarchical scaling, recursion, which is basically what I depicted there. And this is the key difference, right, with Polygon supernets. There are checkpoints in both cases. And I would say we have more, our user experience for cross-net communication should be more seamless than on Polygon supernets. Because what I figured out from Polygon supernets, this is really single hop. And especially in the hierarchy, you might want multi-hop there. Of course, the advantage is this is production already, we are not. And basically, we are again focusing on FVM and IPLD. And another related technology is avalanche subnets, where the difference is slightly bigger. Again, there is no recursion on avalanche subnets. But avalanche subnets also doesn't use checkpoints. Like there is a cross-net messaging protocol, but there is no really disleveraging of security because there is a different design. In order to become a validator on avalanche subnet, one needs to stake AVAX on the primary chain. So that's a bit different of a model, right? So it's kind of very specific to them, and it doesn't allow this hierarchy and basically this division. So you cannot really spawn a subnet without affecting the mainnet. So you need to do stuff on the mainnet in order to do this. So it's rather different. So it's like, I would say, more different than Polygon supernets and IPC. So in summary, I think IPC unique value proposition, especially if you compare to Avalanche subnets and Polygon supernets, is this hierarchy among subnets and recursion, and it seems that this is useful. Again, for gaming and for storage, we do have examples where we want this like to go beyond L2s. And if you want to reuse this, then basically our solution with smart contracts which are deployable on different L1s as well is also interesting, right? So there is this extra plus that we have a design which allows deployability on any EVM compatible L1, and in principle, in Bitcoin, well, of course, it's not deployable now because we just have these two Solidity smart contracts. So it's currently you cannot deploy it on Bitcoin, but in principle you could, potentially. And if you have any questions, I will be happy to answer. Did this help? Yes. Yes.
So you showed the difference between Avalanche, IPC, and Polygon supernets, and I think like we looked on different dimensions here in this table. The dimension I'm most interested in, are these technologies capable of achieving like billions transactions per second? Like, because like that was our KPI, right? Like for the metric, like okay, they have a bunch of differences. They cannot do L3 plus, but can you do this millions and billions transactions per second on Polygon supernets and Avalanche? Thank you.
So I think recursion would help you get there. I think we are not there yet, but I think we have a design that could potentially get us there, right? And it's not that, I mean, they could in future, of course, have this recursion and L3s and whatnot. But, you know, just thinking and designing for that, I would argue that gives us a bit of an advantage because we are designing for those use cases. And this is the motivation, essentially. So like from this motivation stems the design and implementation, like how we did it.
Hi, thank you for your presentation.
Welcome.
Just a quick question. So, if we don't have enough deposit token in the mainnet, right? So obviously we're gonna have a challenge to having the communication with the mainnet, right? I want to know if I don't have enough deposit, would I be penalized for that? And what else? What kind of challenges that I am facing or difficulties? Thank you.
Yeah, so it's important for like you could spawn a subnet theoretically with one fill or even subfills, right? So what you will need is to essentially pay for checkpoints on the parent net. Otherwise, there are no limits whatsoever in how much collateral you need to spawn a subnet. We are not really imposing this. We might have some recommendations, but essentially, like if you want to do it for fun, you can do it now with one fill. What will happen is that you might have trouble when you want to checkpoint back to the parent net. You might have troubles actually paying for the fees on the parent net, on mainnet.
I think it also depends whether you're creating your own subnet or whether you are trying to join an existing subnet that someone else is running. Like if you want to spin up your own subnet for fun, it's exactly what Marco's saying. Like you can do that with very low collateral. No one's going to trust your subnet because you have no value at stake. And so no one will do anything of consequence that they would need that kind of like root security for, but that's maybe okay, depending on your use case. If you're joining someone else's subnet, then they can set requirements of how much collateral is required to join that network as a validator or some other role of consequence that might get block rewards or something like that. And I believe those get locked at the root, right, Marko?
Yeah. So every particular subnet can have its policy, like we don't accept additional validators unless they stake so many collateral. That's fine. So that's a local policy of a subnet. I like to compare that to LLCs, right? So you can find an LLCs, especially in some countries in Serbia, with $1. But if you see this in the registry, right, and you can see that on the blockchain, you might not do business with such an LLC. And I find it a nice comparison.
Yeah, just to give maybe a few more notes on kind of like the vision and like where we ultimately trending towards is if you, as a developer, you start up a highly customized chain with custom consensus, custom runtimes, custom built-in actors, gas policies, and a membership policy for that subnet that maybe gates membership based on latency, geographical location, whatever. It's a highly customized subnet. It's a NAP-specific subnet or a subtree, because that subnet could then spawn off new subtrees depending on like the kind of layout that you eventually want to create and how that subnet in itself is going to scale. At the end of the day, it's like, well, your app is worth, the security of your app is worth as much collateral as that subtree was able to lock up in the parent for itself, right? So now it's entirely up until it's on you to decide like how you're gonna, like how validators in this subnet are gonna join. It could be that some applications, for example, have every single user of their application be a validator of that subnet. So it's a highly democratized model. In other worlds, there could be a small set of validators that are providing like a very strict quality of service to that subnet based on kind of like, those characteristics that you're gating the membership on, and users are just following that subnet, right? So it really depends on like what the security model ultimately for the app is, but that is like one category of subnets. It's like app-specific subnets, but then there are also multi-tenant general purposes subnet, right? Where, say for example, you're setting up a whole subnet infrastructure that has a specific consensus protocol that you're creating, or like a specific idea on how members will come to be, a specific federation, geographical distribution of that subnet. And then you're like creating, in that case, you would be an operator or like creating an infrastructure that is multi-tenant where a lot of any application can deploy, right? So it's not an app-specific subnet any longer. It's kind of like, a cloud facility, so to speak, right, for subnet. So in that case, you probably want to like favor really, really high security, because now all these applications would be secured. You want to demonstrate the value of deploying on your subnet, right? And that this is a strong commercial offering based on the collateral, and that is partly awarded by the collateral that has been locked, because you want application developers to select your subnet, right? You want to attract application developers to select your subnet as a deployment target, right? Or subtree, or kind of like this whole value prop as a subtree, right? So I think like the cool thing about IPC as a framework and in general, like, you know, everything that, you know, is being proposed here is that it's super customizable on all ends of the spectrum, right? And you get like super different formulations of how subnets, you know, could come to be and like what purposes they fulfill.
I'm going to ask my question again, and it's through an increasing fog of jet lag, so forgive me, right? So I still don't quite see how you get to millions of transactions other than the fact that you're creating the possibility for trillions of transactions by getting to millions of subnets, right? Because each one of these, it's parallelism really, even though there's a sort of hierarchical part to it. So have you done is there anything about the way in which you're constructing this that makes the overcoming the problems of computation, consensus, and communication more efficient than it is in any of the existing blockchains out there?
I would say this recursion and the way that we are facilitating cross-net communication is at least a tiny bit better than others. Like, are we going to deploy trillions of transactions today? No. Could this be the basis to go there? I would say yes, otherwise we wouldn't be doing this.
Yeah, the things that I would add, it's not something fundamental to how the chain works that makes the difference. It's the fact that you can, A, spawn more whenever you hit the capacity of your chain seamlessly to increase your space, and B, you can have, in that spawning more, you can bring down your block time to have even faster transactions. You can have more and more and more blocks, and most, you know, if you're just constantly doing a global chain, you're bounded by whatever you can have global consensus over. But the regional design as well allows you that when you spawn your subchains, you can get more and more targeted in the region and the speed at which that chain is moving, which means that you can have even more transactions per second, because you can have, you know, multiple blocks per second with like a sub-second block time, which isn't something you can do if you have a global network that's trying to communicate and come to consensus with like global latencies. So that's interesting as well, but it's not something fundamental to like how transactions are committed into the chain. It's about the recursion and the fact that the recursion allows regional networks, which can have really fast block times.
But the hierarchy also partially orders them, so that helps in some sense. So it's not just parallel. I mean, we have parallel chains today with different L1s and whatnot, but there is some partial ordering, yeah.
Yeah, so that I would add, like, yes, comparable to Web 2 architectures, I think what you're discussing is kind of like what you bring into it is horizontal scalability, right? It's like this, sorry? No, it's great because like, I think one thing where the industry is like not really in general like hitting the marks is like in being able to bring Web 2 workloads into Web 3. So we clearly have to speak about, well, what's working today in the world and why is it like, where is the chasm here, so that like we can, so in many circumstances, it's super useful to talk about Web 2 recipes, concretely Web 2 recipes in Web 2 terms and how those translate into Web 3. And this kind of like technical stack, particularly horizontal scalability, is like what the IPC framework in general gives you by going both horizontal but also vertical through the recursion model, right? Then what needs to, so you can imagine as the activity of a network or an application expands over time and needs to scale, you would spawn vertically and you would spawn horizontally, but then you add the need for what exists in Web 3 in Web 2 to like reconcile a single worldview, in many cases load balancers and things like that, right? And routers, right? So now that is like another primitive that we absolutely need to have to be able to bring, because when you scale horizontally, now you need to reconcile all those clusters into like a single entry point, right? So in some cases, applications can be aware of that routing. In other cases, there might be other routing layers in between, right? I think something that's super interesting is because the consensus of these networks is actually customizable as well. You could think about optimistic consensus models in which you, for example, have subnets that are bound to specific data centers where maybe there's like an assumption of trust. First of all, data center, like if you gate membership of a particular subnet in a data center, and you can do this using networking techniques, you almost guarantee like super low latency between all the nodes. So these nodes can progress really fast in their processing of transactions, right? And you could potentially do an optimistic non-consensus and optimistic like progress of the shared state up until a point where that state needs to be checkpointed, right? That progress needs to be checkpointed on the parent, and that is where consensus collapses. And actually, there's the need to arrive to consensus, not on every block or unit of production, but like only on checkpoints, for example. If that is something that your trust model can assume, right? And it once again depends a lot on the layout of the application, right? So you can imagine this intermix of like private deployments in data centers where there is really low latency between the members and validators, and like because like when we approach Web3 and when we approach blockchains, we usually come at it from the public viewpoint of like completely permissionless and so on, and that means that there is no locality potentially between the members, right? Which adds extra latency into.
Yeah, I get it. Like I think it's really cool. I'm just when we started talking about the trillions of transactions, I started to think about like, well, how many subnets do you need down here at the bottom layer horizontally, and how many in the hierarchy vertically to get to that number of 1 trillion transactions happening across the whole network?